So, about 5 minutes to get here, so we'll get started. So the homework that's due online is homework number 2. Was due on Wednesday. So I probably should have gotten rid of that last week. Homework number 3 on chapter 4 is due on Wednesday, the 24th. Homework number 4 on chapter 5 is due on the 1st. That's next week, Wednesday. We will be finishing chapter 5 this week. We may be getting through most of it today. What should we then do? Go finish typing up all the problems for chapter 6. So we were talking about Newton's third law. So Newton's third law is the principle that forces always come in pairs. Every time you apply a force to an object, it applies an equal and opposite force back to you. So if object 1 exerts a force F on object 2, and object 2 will exert a force, name? Okay. Minus F on object 1. So if you push on the wall will push back on you with an equal and opposite force. I am pushing down on the floor with a force equal to my weight. The force is pushing up on me with a force in the opposite direction. And these are called action-reaction pairs. So the forces are the same size, but the accelerations aren't going to be unless the objects have the same mass. And this means that you can have situations like this, where the contact forces between the two boxes will be different depending on if you're pushing on this smaller box or if you're pushing on the larger box. So here's an example problem. We did do this problem last time. So I'll just go through the calculation. If you have two groups of canoeists that meet in the middle of a lake, after a brief visit, the person in canoe 1 pushes on canoe 2 with a force of 46 newtons to separate the two canoes. The mass of canoe 1 is 150 kilograms. The mass of canoe 2 is 250 kilograms. We want to find the acceleration the push gives to each canoe and the separation of the canoes after 1.2 seconds of pushing. So here, mass 1 is 150 kilograms, mass 2 is 250 kilograms. Force 2 on canoe 2 is plus 46 newtons. We want to find acceleration 1 and acceleration 2. Force 1, to find acceleration 1, we need force 1. We have everything we need to find acceleration 2. So in general, we're going to be using force equals mass times acceleration. Force 2 is mass 2 times acceleration 2. So let's find out force 2 first. So the acceleration will be the force divided by the mass, or 46 newtons divided by 250 kilograms, or 0.18 meters per second squared. Oh, that's right. Now, force 1 will equal minus force 2, because they're an action-reaction pair. So force 1 will equal minus 46 newtons. Force 1 will equal mass 1 times acceleration 1. Acceleration 1 equals force 1 over mass 1. So minus 46 newtons over 150 kilograms, or negative 0.31 meters per second squared. And to figure out the separation, well, canoe 2 is accelerating at 0.18 meters per second in the positive x direction. Canoe 1 is accelerating at negative 0.31 meters per second in the x direction. They both start with the origin. So we know the time in 1.2 seconds. We know x0 equals 0, v0 equals 0. And we're interested in what x2 minus x1 is. So the general formula for x, for back in chapter 2, is going to be x naught plus v naught t plus 1/2 acceleration times t squared. So x2 is 1/2 acceleration 2 times time squared, because x naught and v naught are 0. So 1/2 times 0.818 meters per second squared times 1.2 seconds squared, or 0.13 meters. X1 is going to be 1/2 acceleration 1 times time squared. So 1/2 of negative 0.31 meters per second squared times 1.2 seconds quantity squared. So we're going to get negative 0.22 meters. And the different, the separation is just going to be x2 minus x1. So 0.13 minus negative 0.22, which comes out to 0.35. Any questions about that? The general idea is that when you have two forces acting against each other, force of 1 on 2 is equal to minus the force of 2 on 1. Or on 1 from 2 equals minus the force from 2 on 2 from 1. That's a little closer to what the implication is. So we have two boxes, one large and heavy, the other small and light. They rest on a smooth level floor. You push with the force F on either the small box or the large box. Is the contact forces between the boxes the same in either case? Larger when you push on the large box, or larger when you push on the small box? I'll give you a little while to think about this. Anyone have a guess for this? The way to approach this kind of question is to say, okay, this is the same system, both boxes. So if I apply the same force to it, I'm going to get the same acceleration to the whole system. So in both cases, the boxes will have the same acceleration. In this case, the contact force is accelerating box 1, the bigger box. And in this case, the contact force is accelerating box 2, the smaller box. But the acceleration is the same in both cases. So in this case, the acceleration the force needs to be bigger to achieve the same acceleration for box 1 than over here, where effectively box 1 uses up more of the applied force before it goes on to box 2. That's another way you can think about it. So the magnitude of the acceleration of the system is the same in both cases. The contact force accelerates the box that is not pushed on. Force equals mass times acceleration. It takes more force to accelerate the larger box. the force is larger when you push on the small box. Creation. So here's an actual calculation based on it. We have a mass of 10 kilograms. It's resting on a smooth horizontal floor in contact with a box of mass 5 kilograms. We now push on box 1 with a horizontal force of 30 newtons. What is the acceleration of the boxes? And what is the force of contact between the boxes? So remember, sum of all forces equals mass times acceleration. And force of one 2 equals minus force of 2. Oh, I'll just write these. 1, 2, and 2. So in this case, force 2 will equal minus force 1. And they'll both be the force of contact. So here, let's go over what we know. Our applied force is 30 newtons. The mass of box 1 is 10 kilograms. The mass of box 2 is 5 kilograms. The acceleration of the system is unknown, but it is the same for both boxes. And we know that force 2 is the contact force, and we don't know what it is. But that's what we're looking for. We're trying to find the acceleration of the system and the force of contact between the boxes. Those are the two things we're looking for. So we know in general, for any object, force equals mass times acceleration. So let's look at the forces. We also know that force 1 here equals minus force 2. So force 1 is minus force of contact. So let's write out the forces on the first box. So the applied force, 30 plus force 1 equals mass 1 times acceleration. Sum of all the forces equals mass times acceleration. And for the second box, force 2 equals mass 2 times acceleration. Now, we can substitute in our knowledge for the contact force in both of these. So force capital F minus force F minus force contact equals mass 1 times acceleration, and force contact equals mass 2 times acceleration. If we want to find acceleration, the easiest way to do this is to add these two. And we'll find force equals mass 1 times acceleration plus mass 2 times acceleration. We just added these two equations together. The contact forces canceled out, and we get this. And we find that force equals mass 1 plus mass 2 times acceleration. This is the total mass of the system. So another way you can think about it is that we treat this whole system of two boxes as one big object with mass 1 plus mass 2, and we find the acceleration of that by the applied external force. The acceleration is the applied force over mass 1 plus mass 2. So 30 newtons over 10 kilograms plus 5 kilograms. Acceleration is 2 meters per second squared. Now, if we want to find the contact force, well, now that we know the acceleration, we can just plug it in. Contact force is mass 2 times acceleration. We could also find it by doing a little algebra and canceling out acceleration. We could solve for acceleration and substitute in that equation. So, but the easiest way to find it is just, it's 5 kilograms times 2 meters per second squared, or 10 newtons. If you do want to do it in general, you get, force minus force contact equals mass 1 times acceleration, and acceleration equals force contact over mass 2. So it's in, we have force minus force contact equals mass 1 times force contact over mass 2. And we want to solve for force contact. So we get force equals mass 1 over mass 2 plus 1 times force contact. And so we get applied force times mass 2 over mass 1 plus mass 2 equals force contact. Okay. It's just algebra, but you get that the contact force ends up being equal to the applied force times the fraction of the total mass that the smaller, the further away box is. Now, forces exist in 2 dimensions. So the easiest way to deal with 2 dimensions is just like we did with kinematics. You treat each dimension separately. Turns out you can do force in the x direction equals mass times acceleration in the x direction, and force in the y direction equals mass times acceleration in the y direction. So here, for example, we have campers lifting a food cooler with a weight of 192 newtons out of the reach of bears using 2 ropes hung over tree branches. Rope 1 exerts a force F1 with a magnitude of 166 newtons at an angle of 47.4 degrees above the horizontal, but towards the left, as shown in the sketch, while rope 2 exerts a force of F2 at an angle of 6.1 degrees above the horizontal towards the right. We want to find the magnitude of force 2 that produces a net force on the cooler that is straight upwards. So we know what force 1 is. It's 166 newtons. We want to find force 2 so that the total force on the cooler is exclusively vertical. And we want to determine the net force acting on the cooler, given that force 2 has the magnitude we figured out in part A. So I'll let you guys work on it. But just for reference, force 1 over here is 166 newtons. And the weight is 192. So for part A, we want to figure out what force 2 is such that the net force is vertical. Well, that means our total force in the x direction is 0. So the weight isn't contributing at all in the x direction, so we don't have to worry about that. We know force 1 is 166 newtons. We know the weight is 192 newtons. We know the total force in the x direction is 0. We want to find force 2. We also know the angles. They're in the picture. So we start with the idea that the net force in the x direction is 0. So force 1 in the x direction is force 1 times the cosine of 47.4 degrees, and it's in the negative x direction. So force 1x is negative force 1 cosine 47.4 degrees. That's just trigonometry. Because, yeah, sorry. This is force 1x. And this is force 2x. Force 2x is force 2 times the cosine of 36.1 degrees. The x component of the weight is 0. So let's add these up. Force 1x plus force 2x plus weight x. That has to add up to 0. So negative force 1 cosine of 47.4 degrees plus force 2 cosine of 36.1 degrees plus 0 equals 0. So force 2 cosine of 36.1 equals force 1 cosine of 47.4. We divide both sides by cosine of 36.1. We get force 2 is force 1 times the cosine of 47.4 degrees over the cosine of 36.1 degrees. So that's 166 newtons times cosine of 47.4 degrees over cosine of 36.1 degrees, which comes out to 139 newtons. We also want to find net force in the y direction. Well, force 1 in the y direction is force 1 times sine of 47.4 degrees. Because the net force is the net force in the y direction. So part B is actually asking just what's the total force, because that's the net force in the y direction. Force 1y is therefore 122 newtons, 166 newtons times sine of 47.4 degrees. We can also find force 2y. So that's force 2 times sine of 36.1 degrees. So 139 newtons from our previous answer times 36.1 degrees. So 81.9 newtons. And weight in the y direction, well, that's just negative weight. So negative 192 newtons. So we can add all three of these up. The net force in the y direction is force 1y plus force 2y plus weight y. So 122 newtons plus 81.9 newtons minus 192 newtons. So the net upwards force is 11.9 newtons. Any questions? You can see here we started with the x direction because we knew something about the x direction. Kira, right? So we started with the x direction because we knew something about the x direction, and then we moved on to the y direction. So here we have a 4.6 kilogram sled. then it's pulled across the smooth ice surface. The force acting on the sled has a magnitude of 6.2 newtons and points a direction 35 degrees above the horizontal. If the sled starts at rest, how fast will it be moving after being pulled for 1.15 seconds? The important thing here to understand is that there are some additional forces, but you know the sled is moving horizontally. So the only force you're interested in for the motion of the sled is the horizontal forces. So I'll let you think about that. So, the sled, of course, has a mass, and therefore it has a weight pulling down. There's also a force from the ground pushing up, a normal force. But we're not going to worry about those. We're just going to worry about the horizontal forces because we know the other forces have to cancel out. Because the sled is either flying up into the air or sinking into the ice. And then it's asking how fast is it moving. So remember, velocity and mass fraction, the initial velocity and mass fraction. Acceleration and mass fraction. So we know the sled is moving horizontally. So we're only going to be interested in the forces in the x direction. We're just going to assume all the forces in the y direction cancel out, not worry about them. In the next section, we'll talk about normal forces and the way they work, which is that they cancel out. But we're not going to worry about the forces vertically. We're only going to be interested in the horizontal component. So we know the force being applied. We know the angle it's applied at. We know the mass. We know the time. We know our initial velocity. We're trying to find the final velocity. We're only interested in horizontal motion. So to find the final velocity, we need to know the acceleration. find the acceleration, we need to know the net force. Because this is clearly only moving horizontally, we know the net force is the net force in the x direction. We know it doesn't have a vertical component. So force in the x direction is just force applied times the cosine of the angle. So 6.2 newtons times cosine of 35 degrees, which is 5.08 newtons. Then we can use force equals mass times acceleration to find the acceleration. The acceleration is force in the x direction over mass, which is 5.08 newtons divided by 4.6 kilograms, which gives us an acceleration of 1.1 meters per second squared. Now that we know our acceleration, we know our initial velocity is 0. We know the time is 1.15 seconds. So we can plug that velocity as initial velocity plus acceleration times time. 0 plus 1.1 meters per second squared times 1.15 seconds gives us a final speed of 1.27 meters per second. So the big assumption here is that this sled is only moving horizontally. We haven't quite gone over how you work that out with actual forces, but there is something called the normal force, which resists stuff pushing through surfaces. It is what is holding you up in your chair right now. And that normal force is counteracting gravity and setting the horizontal net force to 0. I mean, sorry, the vertical net force to 0. Oh. So let's talk about weight. The weight of an object on the Earth's surface is the gravitational force exerted on it by the Earth. So, that's the worst eraser. The general definition, the weight, the force of gravity is mass times g, where g is our good old 9.81 meters per second squared. So you are being pulled down by gravity. You have a mass. Gravity is applying an acceleration g. So the force that gravity is applying to you is your weight, which is your mass times g. And that force is pointing downwards. It's not, the general formula for gravity. It's just the weight on the surface of the Earth. Now, your apparent weight can change. Your perception of your weight is based on the contact forces between your body and your surroundings, which means if your surroundings are accelerating, your apparent weight may be more or less than your actual weight. So you certainly experience this when you're in an elevator and the elevator starts accelerating upwards, you feel heavier slightly. And then when the elevator slows down to come to a stop as it's moving up, you'll feel lighter slightly. Or if you've ever been on like a drop ride, while you drop on a drop ride, you feel weightless because your surroundings are accelerating. So if your surroundings are accelerating, you will feel more or less apparent weight than your actual weight. And your apparent weight is just, the force required to give you that acceleration. So we'll have some problems where we'll actually calculate it, but it turns out it's basically mg plus mass times acceleration. Because your acceleration, g is effectively higher from your point of view, or lower. as the case may be. So here we have a problem with weight. The fire alarm goes off. A 97-kilogram fireman slides 3 meters down a pole to the ground floor. Suppose the fireman starts from rest, slides with constant acceleration, and reaches the ground floor in 1.2 seconds. So the useful equation here is going to be, y is v naught is y naught plus v naught y t plus 1/2 acceleration y t squared. And we want to find what was the upwards force exerted, F exerted by the pole on the fireman. So for this, to figure out the upwards force F exerted on the fireman, you need to know, well, you know the fireman's weight. You can figure out the fireman's weight from his mass. And you want to figure out the total force. And to find the total force, you use the acceleration that you'll work out from the distance traveled in the time it took and that you started at rest. So for this, you know the mass of the fireman, the distance the fireman travels, the displacement of the fireman, delta y, the initial velocity of the fireman, which is 0, and the time it takes to travel that displacement. So you want to find the upwards force F exerted by the fireman. We'll give you a few minutes to work on that. So let's figure this out. Our initial position is 3 meters. Our final position is 0 meters. Our mass is 97 kilograms. The time it takes is 1.2 seconds. Our initial velocity in the y direction is 0. We know g is 9.81 meters per second squared. We don't know what the force from the pole is, what we're trying to find. We don't know what the acceleration of the fireman is. And we kind of need to know what the net force is. So to figure out the acceleration of the fireman, well, y equals y naught plus b naught yt plus 1/2 acceleration in the y direction times t squared. We can use this information about distance traveled and the time and the initial velocity to find the acceleration. So the acceleration in the y direction is 2 times y minus y naught over t squared, because v naught y over t is 0, so it just goes away. So 2 over 0 minus 3 meters divided by 1.2 seconds squared gives us an acceleration of negative 4.2 meters per second squared. Fireman is traveling downwards at 4.2 meters per second squared. So we know our net force equals mass times acceleration. Our net force is the force from the pole minus the weight of the fireman, mg. So force from the pole minus mg equals mass times acceleration in the y direction. So force from the pole equals mass times acceleration in the y direction plus mass times g. So mass times the sum of acceleration in the y direction plus g, or 97 kilograms times minus 4.2 meters per second squared plus 9.81 meters per second squared, which comes out to a total force of 540 newtons. So the thing about apparent weight minus actual weight equals mass times acceleration. So apparent weight equals mass times acceleration plus actual weight, which is mass times acceleration plus g. Now this is down. Mass times acceleration plus mg. So apparent weight is mass times acceleration plus g. Modify g by the acceleration. If the acceleration is negative g, then your apparent weight is 0. You're weightless. That's how you achieve weightlessness in space, for example. So the force from the pole is 540 newtons up the positive y direction. Any questions about fireman and pole? Nope. So here we have an apparent weight problem. Part of an attempt to combine physics and biology in the same class, an instructor asked students to weigh a 5.2 kilogram salmon by hanging it from a fish scale attached to the ceiling of the elevator. What's the apparent weight of the salmon if the elevator is A at rest, B moves with an upwards acceleration of 3.5 meters per second squared, or C moves with a downward acceleration of 2.3 meters per second squared. So this will be apparent weight formula is helpful. So let's start with what we know. We know the weight. We know the mass of this fish is 5.2 kilograms. So apparently, I copied this and didn't fix that. Just a second. Let me quickly fix this because I expect that's the only one. Yeah. So we know the weight of the fish is 5.2 kilograms. These are the mass of the fish, not the weight. The weight of the fish is 5.2 kilograms times g. G is 9.81 meters per second squared. We're trying to find the apparent weight in 3 different situations with different accelerations. So in general, force equals mass times acceleration. The net force equals the apparent weight minus the actual weight, which means apparent weight minus actual weight equals mass times acceleration. We can substitute in mg for actual weight and then solve for apparent weight. Apparent weight equals mg plus mg plus mass times g plus mass times acceleration. And then we can combine like terms. Apparent weight is mass times g plus a. Mass times g plus acceleration. So in the first case, if the elevator is at rest, acceleration is 0 meters per second squared. So apparent weight is going to be 5.2 kilograms times 9.81 meters per second squared plus 0 meters per second squared. It'll just be the actual weight of 51 newtons. So 51 newtons in the positive y direction. For B, apparently I also screwed this up and didn't notice it when I was fixing it earlier. So let me freeze this and fix this. Jeez. I will re-upload these slides, fixing these typos. Yeah. So for B, acceleration is plus 3.5 meters per second squared. So we plug that in. Apparent weight is going to be 5.2 kilograms times g plus 3.5 meters per second squared. If they're accelerating upwards, your apparent weight will be larger. So the apparent weight larger will be the larger 69 newtons, or 69 newtons upwards. And for C, accelerating downwards at negative 2.3 meters per second squared, 9.81 meters per second squared minus 2.3 meters per second squared times 5.2, which is 39 newtons. So 39 newtons off. Any questions about that? The general formula for apparent weight is over there. So if you ride in an elevator moving upwards with constant speed, will your apparent weight be less than, greater than, or equal to your actual weight, mg? What do people think? They're in an elevator moving upwards at constant speed. Will Will it be 1, the elevator is going upwards. This will cause a person to press down harder on the floor, giving a apparent weight greater than mg. 2, the elevator moves with 0 acceleration, and therefore the apparent weight is equal to mg. Or 3, because the elevator is moving upwards, it's partially lifting the person, resulting in an apparent weight less than mg. Which of these do you think is correct? So who thinks the apparent weight will be greater than mg? Who thinks the apparent weight will be the same as mg? Okay, that's the yes there. And who thinks the apparent weight will be less than mg? Well, the people who responded were correct. The elevator is moving with 0 acceleration. So you plug 0 acceleration plus g, you get mg. If you're moving with 0 acceleration, your weight will be just as if it was standing still on the surface. Let's see, how much time do we have left? I will introduce normal forces, but I won't go through any problems. And we'll go over this again and continue this on Wednesday. So the normal force is the force exerted by a surface on an object. So the force that's holding me up as I stand here on the floor is a normal force. It's called a normal force because it is perpendicular to the surface of the object. It is normal to the surface. So here, if you have a can of beans or a can of tomatoes here sitting on a surface, the normal force is pushing upwards to keep the surface from entering the surface. Here we have a suitcase. The normal force is pushing upwards to keep the suitcase from entering the surface. The normal force acts with an amount of force necessary to keep the object from having an acceleration or any movement into the surface. It prevents you from passing through the surface until you exceed the strength of the surface and it breaks. So the normal force can be, if you have just something like, my cup sitting on the table. In this case, the only forces acting on it are gravity and the normal force. And it's not accelerating anywhere. So in this case, the normal force is equal to the weight. But the normal force can be equal to the weight. It can be greater than the weight. If I push down on my cup, the normal force is going to have to get bigger to counteract the force I'm applying downwards, or less than the weight. If I lift up on my cup, the normal force will be reduced. So it's adaptive. The normal force will be big enough to keep the object moving through the surface. So generally, the normal force will counteract all forces going into the surface. And it's always perpendicular to the surface. So if you're on an inclined plane, on a slope, like here, the normal force between my clicker and the ruler is not vertical. It's pointing out this way. It's perpendicular to the slope. So if I let go of this, it gets an acceleration from the portion of gravity that is along the slope. So that means when we're dealing with slopes, it's often very helpful to do a change of basis and change from being having x and y be horizontal and vertical, and instead have x and y be along the slope and perpendicular to the slope. Because this makes dealing. So in this case, the normal force, which you don't necessarily know, ends up being perpendicular to the slope. And so it's in the y direction, is easier to work with. While you do know the weight pulling down usually, and so you can break that into components down the slope and perpendicular to the slope. And it turns out it makes problems easier. It's not impossible to do the problems with, y being vertical and x being horizontal. It's just easier to do it by rotating the coordinate system in a changed basis. So yeah, this is tricky problem. So here, for example, in this problem, it's easier to just work out in the in the basis of up and down the slope, because then it's easier to figure out the acceleration down the slope and the acceleration perpendicular to the slope. But now I will go away. So that is all we're going to cover for today. I'll see you guys on Wednesday. We'll continue on with normal forces. And we'll finish up chapter 5 and start chapter 6. So I need to get on writing up the problems for chapter 6.